Hi, this is Mark Struthers. We're doing another quick presentation. This one is Quick MRI, which looks at the fundamental concepts of producing an MR image. Basically, an MRI is nothing more than a giant magnet set to align all of the protons in the body between north and south. When the patient goes into the MRI magnet, all of their tissues are magnetized, and the tissue protons align with the magnetic field in the north and the south direction. Here we can see how they align in the field. Hydrogen protons are most abundant in the universe, with the hydrogen protons in the body aligned either to the north pole, which would be positive, or the south pole, which would be negative, of the magnetic field. Almost all of the protons cancel each other out. Plus 1 minus 1 equals 0. Fortunately, a few more protons align with the North Pole because it has lower energy, and these are what we work with when we create MRI images. When aligned with the magnetic field of an MRI, the protons spin at a frequency that corresponds to the magnetic field. The higher the field, the higher the spin frequency. When a hydrogen proton spins at 0.5 Tesla, it definitely has a different frequency compared to spinning at 3.0 Tesla. The higher the frequency, the higher the signal strength, so therefore there's less time needed to gather the information needed to create images. The MR magnet is always on, so when the patient leaves the magnet, then the protons return to their original state. In their original state, the protons wobble very similar to the Earth rotating on its axis. This is known as precession both for the Earth and for the protons. Once the protons are aligned in the body, they're all the same energy. And how can we measure the differences in tissue energy using MRI? Here we can see a snapshot of all the protons aligned, north and south, low energy and high energy. As the protons align with the magnetic field, they align in one of two orientations: parallel, north positive, and anti-parallel, south negative. In a 1.5 strength Tesla magnet, there might be 9 protons more aligned to the low energy field than there is to the high energy field for every million protons. These can be energized to create our image. The protons spin at a frequency that corresponds to the magnetic field. The higher the field, the higher the spin frequency and the more strength in the signal. Actually, they don't spin, they wobble like the Earth on its axis. This is called precession. In the magnet, they all precess at the same rate. So how can we measure energy and differences in tissue? Well, as we know, MRI locates and measures areas of natural occurring substances to form an image. Using RF signals coming off the gradient, we can push those 9 low energy protons down into the high energy area and then release the energy. The energy released by the protons as they return to their natural state is exactly proportional to the tissues that they represent. Different tissues absorb different energy from the RF pulse, and when the pulse is terminated, the tissues release that energy that they had absorbed. The energy released by each tissue is unique, as each tissue has a unique proton structure. The released energy is used to create the MR image. A simplistic analogy would be when you did an X-ray and the tissue absorbed the energy, the amount of energy absorbed was related to the tissue it went through. The ionizing radiation that penetrated the patient was then utilized to create an image. Just as the strength of each of the tissues' released energy creates an image in MR. So how do we map these images? Well, very simply, we superimpose another magnetic strength over each of the different planes, axial, sagittal, and coronal. This strength is released in a gradient or a slope, very low energy to very high energy. This allows us to measure all of the energy levels along the slope for, say, an axial image. We then do the same thing for a sagittal, and then we do the same thing for a coronal. Adding all three of those points together, we can map the energies to create our image. Here we see the axial, sagittal, and coronal gradients being applied, superimposing their energy over the original energy of the magnet. Again, they are heterogeneous and not homogeneous, and they are on a gradient or a slope. This allows us to pinpoint or map the tissues in the body. Here we can see the different gradients, and when you're in the magnet, you can hear them being applied. They have that knock, 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 knock noise. This is the sound of power being applied at one end of the gradient and then power being applied at the other end of the gradient. The power applied at each end is different, therefore we get a slope. We can map the body because each point in the body will contain all three magnetized planes: the Z or axial, the Y or coronal, and the X sagittal at that specific reference point. At isocenter, we can choose one plane as the image slice, the second plane as the location of the slice or the frequency, and the third plane as the intensity of the slice or the signal or phase. So let's say we have an axial image at this point and at this intensity. That intensity gives us a shade of gray, which corresponds to the tissue density. We then just map the densities onto a matrix, and we have an image. So a quick recap. MRI has the ability to image in different planes. These planes are defined by using the three-dimensional Cartesian coordinate system: axial, sagittal, and coronal. We apply gradients to put a different slope on the already magnetized protons in the body so that we can pinpoint where they are exactly and map them into an image. This is Mark Struthers, and thanks again, and we'll see you soon.